So I'm doing this without checking CVs or notes or anything at all, except just to say that Imon worked with the
recording in progress.
Imon worked with the AIMI Center and with IBIIS division for many years in a number of capacities, and did fantastic work in machine learning and AI with Daniel Rubin and Matt Lundgren and many others of us. Including natural language processing projects, including computer vision type projects. She was a sought after mentor for many of our students and really helped a number of folks more junior to her come up as well. And we were sad to lose her to Emory University, but also with mixed feelings, very happy to see her with an assistant professor position there and growing with the amazing informatics team and AI team that is at Emory now. And so really looking forward today to hearing from her on the fusion of multimodal data for clinical event prediction and simulating physicians' workflow. So Imon, thank you so much for being here.
Kurt, thanks for doing the intro. I'm sorry I was held up in another meeting. I really appreciate you jumping in.
Sure.
Thank you, Kurt. Thank you, Daniel, for the introduction. So yeah, so this slide is not really necessary. So I just wanted to tell you that I started this work actually when I was in Stanford. I'm still collaborating with Stanford and working on multiple different projects with this IBIIS and AIMI group. So conflict of interest, none. So let me tell you, I'm not a physician though, but I work very closely with physicians still, like many oncologists, radiologists, cardiologists, especially in Emory. That's the only thing I got. Like I'm working very closely with cardiologists too. But let me give you an example of a cancer patient that when the cancer patient comes in and he or she actually analyzed through different modality, right? So you can imagine that they have the radiology imaging exams, and that generates not only images, but also generates the text data. Then the patient goes and to the pathology exams, and it generates also the imaging data as well as the clinical note data. Then they have all the other type of structured information like the electronic healthcare record data, like lab, medication, records, and multiple other things, right? And overall, actually, we also have the temporal clinical notes, which is like expert interpreted data and knowledge. So expert actually looks at the patient, does analyze the symptoms, and also analyze the other types of imaging and the laboratory test, and then decide their own findings, summarize the symptoms, summarize the treatment plans in the clinical notes. So clinical note, which is like is a temporal data, like every time whenever the patient actually goes to any kind of clinical encounter, it also generates the clinical note, and that is a very, very rich temporal data that is captured and stored within the electronic healthcare records. And finally, when the oncologist or any physician views the patient, the task is to actually digest all these different types of data source, starting from imaging, reports, other clinical notes that was recorded or documented before even the patient comes to the oncologist, along with this kind of laboratory and medication data. So as you can imagine that given all these huge data sources and heterogeneous data source, it's very difficult for any physician or oncologist to digest this data and make the diagnosis or make the treatment plan based on all these different data sources. So often what happens is that the physician or oncologist just analyze the data from the few recent time points and make the diagnosis only based on that. For example, if that cancer patient has a history of the data in the same electronic healthcare records, like 10 years, of course, the physician or oncologist doesn't go back to 10 years. It just analyzes the few recent time points. So that's like more or less the workflow currently in the clinical scenario. But when you see the machine learning literature for diagnosis and prediction, we have a very strange division. That the first division is that we build the machine learning model on the imaging data. So we have the radiology images that goes inside the machine learning model, and we predict the diagnosis or we predict the future clinical events, right? Then also the pathology image goes into the machine learning model. We do the similar thing. Very rarely, actually, the pathology and radiology images are analyzed together. Then, for example, that we have another huge domain, which is the machine learning model developed on only in the electronic healthcare data. By electronic healthcare record data, by that actually I mean mainly the structured data, like laboratory values, medical prescriptions, then patient demographics, clinical comorbidities, and then it goes inside the machine learning model, and you do the similar thing with sometimes even the same task. But of course, there are also model develops that works on the clinical node data, that parse the clinical node, also make the diagnosis and prediction. But as I was telling you before, that it was very rare to combine all these data sources in the same machine learning model to do the diagnosis and prediction. People will be like very arguable with me that why do you need data when imaging gives us very good performance, like, I don't know, maybe like 90% accuracy on a particular diagnosis stats. Why do we need all these types of data? Because physicians actually are analyzing those data, and maybe for some cases, which are very rare cases, okay, machine learning model perform very well for the common cases probably, but for the rare cases, maybe those extra data or extra information about the patient clinical history or demographics may help to reduce the bias in the machine learning study. So when we look, actually, this is a study with Matt. So when we look actually on all the study that was published before, we saw that, of course, starting from the year when the deep learning became popular, the study of the machine learning with the different modality is becoming increasing day by day. For every year, you can see that a kind of like exponential growth. But when you look at the fusion model, that whenever any deep learning model that try to merge different sources of data, as you can see here, okay, it is still growing, but still is very, very few in numbers compared to the model that was built on single modality data. By fusion model, what I mean is the model that is following one of this architecture. So either the early fusion, when they merge these two data sources early in the model development and then train the model, and the loss will be propagated to this particular layer just before the early fusion, right? And then there is also joint fusion when the model has two different branches, and each branch actually read one different types of modality. And finally, when you calculate the loss and you do the backpropagation, so the loss will be coming back to each of the branches of the model. Sometimes we also see this kind of joint fusion, which is the type 2 joint fusion, when the loss is only coming back to one particular branch, but not coming to another branch, because probably this branch is just demographic data, doesn't need the loss propagation on this particular branch. Then we also have the late fusion. So most popular model you will see currently to date is the late fusion for model development, because it's a kind of independent model development. When there is no backpropagation of the loss, the two models are trained independently on two different data sources. And finally, actually, we are just training another meta classifier on top of the score predicted by the two model and do the prediction. So by fusion, we are accounting all these different types of model. So when we start actually looking for different papers published, we saw that only 17 papers actually qualified our criteria, that actually using at least one of the imaging data that merge it with the EHR data and finally do some kind of diagnosis and prediction. We can only see that only 17 qualified the criteria when we do the search on PubMed, Scopus, Google Scholar, and all these popular platform. But this is surprising that fusion is like so popular in the clinical workflow, but not similarly popular in the machine learning workflow. Because one reason could be that actually fusing this kind of heterogeneous data, as you know, that clinician does very hard job actually to merge all these types of data. But for machine learning, it is even more harder because they are heterogeneous type, there is missing modality, there's missing data. So because of that, actually it became more and more hard problem. So the first thing that we try to solve or try to attack with this multimodal fusion is the breast cancer recurrence. So probably you guys know better than me because most of them are clinicians, and you know that though breast cancer has a very, very high survival rate if it is diagnosed at an early stage, for example, like stage 1, stage 2, stage 3, but if it goes to stage 4, which is a distant metastatic, the survival is only 22%. And breast cancer is like one of the most common malignancy among the female patients, most common cancer malignancy among the female patients. So it's kind of like very serious and it needs to be addressed quickly. And there is another interesting statistics actually. So if you look at incident versus mortality, you'll see that even if the rate of incident is very high on the non-Hispanic white population, but the mortality is higher in the African American patient. So it's kind of like interesting statistics. So, but the problem is that we need to dig deep and understand what actually bias these kind of statistics, that why the mortality is higher in the African American population. But the problem is that the population-based US cancer registries like SEER, they are funded to collect the data only for the fast course of cancer therapy and cannot conduct the continuous follow-up. So we need some automated method, and to do this kind of continuous follow-up, it's very laborious and time-consuming and very expensive process, also from the national registry, also from the state registry. So we need to solve this problem and do some automatization so that this kind of outcome data can be curated automatically. So what we develop is, we developed an NLP pipeline, though it is not really merging imaging data. We developed an NLP pipeline that merged the radiology report, pathology report, and progress note from the 10 years breast cancer patients from Stanford. Probably you guys know the OncoShare database. And what we try to predict if the patient has recurrence at every quarter. So basically we divide the whole patient encounter timeline into multiple quarters. For example, this in this example, I'm showing from Jan 25 to 26. And we are just dividing that based on quarter. And if every quarter the patient could have pathology report, radiology report, progress note. Even if one modality is missing, it doesn't matter, because that modality will be completed by the other modality. For example, if the patient doesn't have a pathology report, our model is not affected by that, because if the patient only has progress note, still the model can work only on the progress note. So we create like a text snippet from every quarter, and then we pass it through the deep learning model, and we predict if the patient has the recurrence in that particular quarter. And the model was trained on this many number of reports, more than like 130K reports, and tested on 34K reports. So we also compare our model on the baseline rule-based system, which was also developed and published earlier. And we show that this kind of model actually performed very well for identifying the definite recurrence versus no recurrence. And also the patient level performance was very higher. So when I showed this performance, this is actually identifying the timeline of recurrence, but we also predicted that the patient level performance, if this particular patient has recurrence or not. So the performance was very high on that sense compared to the rule-based system. As you can see here, the rule-based system has only 0.2 specificity, while our model for the definite recurrence is 0.82 specificity, which is pretty heavy boost. And just to show you kind of like interpretability part of the model, now this is the rule-based model. The rule-based model is actually having problem in identifying very vague sentence. For example, a tiny metastatic focus, difficult to exclude. The model is predicted as recurrence present because it says tiny metastatic focus, but difficult to exclude, this kind of vague sentence, the model failed to identify it as no recurrence. It predicted it as recurrence present. But the neural recurrence model actually can identify and put correctly the weights on the words like finding, pulmonary, multiple, this kind of word rather than metastatic. So you can imagine that if finding actually tell us there is a definite finding of recurrence. For example, worrisome, which is a no recurrence, that the physician is just worried about metastatic, but no metastatic was yet definitely established. The model also put the high weight on worrisome rather than metastatic. So it's kind of like interesting that the model also identifies this kind of like vague sentences. So after that, actually, so we established this kind of cohort and we automatically annotated the recurrence for the 10 years breast cancer patient data in Stanford. But this is helpful for the machine learning model training or building afterwards, but this also is helpful to build the patient timeline. So for example, this is an example that we took one random patient and we parsed all the radiology pathology report of the patient. And as a result, actually, we draw a kind of timeline of recurrence for that patient. Not only timeline, we also identify the sentence actually where the model put the highest weight. So the weight, the sentence is malignant neoplasm metastatic to brain. So malignant neoplasm metastatic to brain, actually this word is coming from the progress note, not from the pathology report or radiology report, because the patient has the pathology and radiology somewhere outside Stanford. So this is pretty interesting. The model can also identify this kind of like words even from the progress notes, and also shows this kind of in a graphical user interface that, okay, so this is the word and this is the date of recurrence. as I said, like this is not only for patient by patient analysis, since we did the annotation for the whole cohort. So now we can slice and dice the cohort as we want. So we slice and dice based on tumor grade, tumor receptor, shows that how the recurrence, how the tumor receptor has the effect on recurrence. But as a machine learning model developer and the computer science passionate people, my main interest is actually this, that the model also was generalizable well to the prospective breast cancer cohort from Stanford, because we trained the model till like 2019 data. But what we did, actually, we tested the model from 2019 and 2020 data, which was not included during the training. And we show that the model performed equally well on that prospective data set. As well as, since metastatic is more general, not only like primary, it doesn't have too much effect on the primary side, we also tested the model on the liver. We got 0.95 AUC-ROC. So it shows that the model trained on only one primary site is also extendable to a completely different primary site. And then actually we compare the model performance, compare with the ICD-9, ICD-10 codes, because ICD-9, ICD-10 codes also has the structured levels for metastatic recurrence. And we compare that with the ICD-9, ICD-10, as well as we compare that with the California Cancer Registry data. And we show that the model has the highest coverage for identifying recurrence compared to ICD-9, ICD-10, or California Cancer Registry. And only 5 patients that has ICD-9, ICD-10 identified as recurrence, but the model didn't identify as recurrence because those patients doesn't really have any clinical notes that we can identify. So probably we are missing some clinical notes, or some clinical note was lost or not saved. But in CCR, actually, there is 90 extra patient that was not acquired by the model because those patients has recurrence outside Stanford. So they left Stanford and start doing treatment somewhere else. So that 90 patients was not acquired. I'm sorry, give me just 1 second. Sorry for that. Then the next thing is that we trained the model, as I said, only on the binary classification task. So the model was trained only for the distance recurrence versus no recurrence. Then we were curious how the model will behave on the local recurrence cases. So we just plot the predicted probability value on the breast cancer prospective case, and we clearly show that the model actually can identify local recurrence versus distance recurrence, because those 2 bar plots are, you see, like they are far away, especially if you compare the mean. So that is pretty interesting results. So we start doing the similar thing with the liver, local recurrence versus distance recurrence. We clearly see that the model doesn't really work that well, similar to breast, because in liver, actually, even if the metastatic occurs after the liver transplant, but still that they consider as a distance recurrence because it is not in the same liver. So it's a kind of confusing language. So because of that, actually, the model prediction for the local recurrence and distance recurrence is not like equally spaced. But so even in the liver, probably it's not possible for the local recurrence and distance recurrence identification. But for breast, it was clear that the model can identify local recurrence versus distance recurrence. The next obvious task is that when we identify the recurrence, can we identify the site of recurrence? So we also take the snippet that was tagged as positive recurrence. We develop a model like 7 different models for different anatomical site to predict the site of recurrence. So now actually we have one model that predict the recurrence, and then we have, starting from that decision point, we have 7 different models that predict the site of recurrence. So this is the result. Again, the model was trained only on the breast retrospective cohort, and we tried it on the breast prospective and the liver cohort. And we clearly see that model performs quite well for all these primary sites. The bone, liver, lungs, all these primary sites, the model performed pretty well. Also for liver, the performance was pretty good. But how we can use these labels? Okay, so of course we can store this label in the cancer registry, and it actually reduces a lot of human curation tasks. But can we use that on the machine learning model as a weak supervision? So we actually trained a mammogram model with the recurrence level extracted using the NLP. So we have a set of recurrence level that was actually curated by the expert annotators like radiologists, as well as we also have their recurrence and no recurrence levels extracted from the NLP model. And it's a simple CNN model. And this is the results. I don't want to go into too much detail of the model, but I just wanted to show you the result. So this is the result actually. We trained a model separately with manually curated level, but we only have 1,000 exam with a manually curated level. But when we actually use the NLP to generate level, we have more than 80,000 exam. And in that, actually, we got very high performance boost compared to the baseline method when it was only curated manually. So it's clear that even though weak learning, weak supervision doesn't give us like 100% performance, but still these kind of levels are very pretty good compared to training on a very small data set using manually curated levels. Of course, the next obvious step was, other than doing just the label curation, can we predict the temporal event? So the whole idea is that, as I told you before, the whole idea is the patient comes in with a visit note. We do the prediction for that particular targeted event that we want to do prediction. The patient comes in to the next clinic visit. So he or she has a previous visit and the current visit, and we do the prediction using both these time point data, but weighted differently. Then, of course, the patient comes in a third visit. So we have 3 visits. And similarly, we have n visit with all the previous visit. We consider the current visit note as well as all the previous visit note. And given that we have a lot of like interesting embedding techniques, especially we also develop an embedding technique with semantic dictionary mapping. So this kind of embedding technique actually helps us to represent this visit note into vectors. And once this visit note is transferred into vectors, it is possible to build this kind of like temporal model that read this visit note sequentially and predict the clinical events for every time point. So the first thing, again, of course, as I said, like breast cancer is my favorite use case always. So first thing we present is that we predict the recurrence using the NLP level as well as the manual curated level, same as the mammogram task. But here the task is just using the clinical encounter data. So we have a prediction time point 1 year before the recurrence occur. For some patient, it will be positive that the patient will not have recurrence. For some patient, it will be negative, the patient will have recurrence. Here, another challenging task is that we don't have the similar visit for every patient. So some patient starting from the diagnosis stage, some patient has radiology exam, surgery, some patient doesn't go through surgery, go through another types of treatment. So every patient, the treatment and their demographics, their previous comorbidities is completely different. So that's kind of thing makes the problem even more challenging. So we build a recurrence prediction model. Again, it's a kind of like very standard processing step. But only thing is that we use actually the weak labeling, where we use the manually curated data along with the NLP generated levels to increase our data set. And finally, we evaluate the performance. So again, we have a temporal model which reads these vectorized clinical notes. For each time point, we have a 2-layer stacked LSTM, and then we finally do the prediction for each of the time point. So as you can see here, this is actually the prediction generated by the model. So the blue line actually represents the model prediction, and the red line shows the ground truth. So 0 means the patient doesn't really have prediction after 1 year. And when it switched from 0 to 1, that means the patient have recurrence after 1 year, starting from this particular time point. And you see that the model prediction actually closely follows the ground truth. That means the model prediction was quite good for identifying the recurrence in 1 year, just by reading the clinical notes. Then we actually did the comparison, again, similarly as a mammogram study, that only with manual annotation, we got 0.84 AUC-ROC. And when we add the manual annotation plus NLP generated annotation on the training, and using the same test set, we got 0.94 AUC-ROC. So it's, again, a good boost. And then we compare the 3 different strategy, plus this traditional supervision only with manually annotated levels. So we got 84. Then we did weak supervision 1, which is the best trade-off between sensitivity and specificity on the NLP levels. Then in the weak supervision 2, where we increase the specificity but decrease the sensitivity. So we got like 0.94. It gives us a little more number of recurrence cases, because that was we are missing. And then we compare with also the traditional model like XGBoost, which is also a very powerful model, and the performance boosted from like 0.81 to 0.94. Following the same strategy, actually, this kind of like temporal prediction, we handle another use case, which is again only with clinical notes. We predicted the survival of metastatic cancer patient. because we know that if we give the patient very overly aggressive treatment, the patient may not survive anyways. And another problem is that the life expectancy of the patient or the life quality of the patient will also decrease. So we need to develop a machine learning model that can predict the survival 3 months before, so that we can tune the treatment based on that. So again, we have the similar pipeline. So we have the vectorization of the clinical node and 2-layer stacked CNN, and we do the survival. And we have this particular data set, which is again kind of like significantly large data set, where we have more than 13,000 patients in the training and 899 patients in the testing. And we are all different kind of primary sites and all different kinds of nodes, like oncology node, progress node, radiology report, discharge summary, nursing node, and everything. And this is the performance actually that we got 0.89 AUC ROC for the 3-month survival. And when we stratified by different primary site, we also got like very high accuracy for most of the primary site. Only head and neck was 0.82 because we have very few patients on the head and neck category. And when we compare that actually with the physician success rate is 0.7 AUC. Compared to that, the model performance is quite high. We also develop a graphical user interface where the physician can click on each time point, and the model will tell us like what are the types of the clinical nodes the patient has at that particular time point, and what are the most interesting findings from that node based on which the model is making the decision. So as you can see here, the prediction closely follows the ground truth, and patient has a diagnosis of metastatic to liver, then the chance of survival is going down, starting from the critical care node where there is urgent period of hospitalization, poor PO intake and everything. But sometimes the model doesn't succeed that as well as this graph, because this is a case where the model kind of failed because the model is predicting the patient is not going to survive, but the patient actually survived. The patient is not going to survive because this kind of temporal model has also a kind of drawback that if you don't have sufficient preliminary previous data in a sequential model, starting from the first time point, if you start prediction, of course, the model will think that there is a diagnosis node, then there is an urgent period of hospitalization where the patient is not doing good. The model will think that the patient is not going to survive because it doesn't really have any previous time point data. This is the first time point data with the diagnosis. But then when the model has a lot of preliminary previous data, and it comes to a progress node, says they're doing well without complaint, the model prediction again went up. So this is a kind of risky scenario that the model should have a kind of like number of preliminary data before even start making the prediction. So this is with the clinical nodes. Then we also started doing the similar multimodal prediction model with the COVID for resource utilization, where we want to predict if the patient will stay self-isolated or the patient need hospitalization within 7 days. But again, there is a similar problem. The patient has a lot of encounter history as well as the current encounters also. And we consider actually the RT-PCR test time point as a prediction time point. So we consider all the patient who has RT-PCR positive test results. And we are only using the structured EHR data for this case, but coming from different modality like lab values, medications, demographics, and everything. So this is a kind of like flowchart for our patient. So we have total 3,000 COVID patient that has RT-PCR positive test results. So when we consider only a positive test result, we have 3,120 patients. Then we only consider the reason for admit when the patient has a reason for admit COVID. And then there is 1,340 self-quarantine and 1,504 hospitalized patient. And then we also have the ICU admission, but we are not considering the ICU admission for this particular case study. Again, we develop this kind of like early fusion and late fusion model. Early fusion model, we are just concatenating, is a very standard representation of any EHR model that we are concatenating all the vectors together. And finally, we are doing early fusion with an artificial neural network. But then we also have a late fusion model where we are not concatenating each of the data streams. So we are considering each data stream separately through a neural network, finally combining that and develop another neural network on top of it. And we are doing backpropagation of both of the neural network there. And this is the result actually. So we consider the PR curve as well as the ROC curve. So we shows the individual modality results as well as the fusion result. So as you see that for the individual modality, surprisingly, the CPT score performance is pretty good. CPT score performance is very, very good because the self-isolation versus hospitalization, if the patient has diabetes, like renal disease, so this kind of procedure with CPT actually is highly influencing the prediction. So because of that, the CPT got high score. But if you see that early fusion and late fusion actually overcome the CPT performance and give better performance, even middle fusion give us the better performance than any of the single modality model. So this is a pretty interesting observation. So we also stratified the results based on the race, based on age, based on gender, based on race. Actually, we don't see a lot of difference because between the African American and white population, because we see that in Emory, this is a kind of like specialty that we have almost 50-50 distribution between African American and white. So we don't see a lot of performance difference, but Hispanic performance dropped a little bit because we have less number of Hispanic patients here. Then for the age, it doesn't really have too much effect, but we only have effect for the age less than 30 years, because most of the patients less than 30 years of age who has COVID doesn't really have hospitalization. So the model really learned that very quickly and got very high accuracy on that. So this is actually a study with Matt. So this is the most important study because we actually integrate the imaging data with the EMR data with this study for diagnosis of pulmonary embolism. So the whole idea is actually we want to identify the P positive versus P negative. So we build separately a model for EMR only. So just using the EMR data, then we combine it with the image only model and we describe the performance. And this is our performance actually. We clearly see that it's a late elastic model actually gives us the best performance than any of the single modality data, even if we know that actually for the P diagnosis, this radiologist look at the CTA exam and does the diagnosis pretty well, but still for the machine learning model, EMR plays a very critical role, and the boost of the performance is obvious that we got very good boost of the performance compared to the initial imaging model. So that is pretty interesting and interesting results actually. And so this is, we compare actually define fusion architecture for this particular model, and we clearly see that here also in this particular task, the late fusion model is working pretty well compared to like joint fusion or early fusion. But for the sensitivity wise, early fusion also performs quite nicely. So following the similar architecture, we did another study with macular degeneration for the eyes, where we have SD-OCT images. So we also have the temporal SD-OCT images. Compared to the previous study, this study interesting in the sense that we also have another dimension, which is a temporal dimension, because for this particular disease, the patients start losing their vision day by day, and you see that they will have this kind of like black spot in their vision. And when this black spot is detected, it's like already like in a very late stage of AMD. And so the early detection and early identification of AMD may stop this kind of like very late stage, going to the very late stage. So the whole idea of this project is actually to predict the AMD at least few years in advance, so that we can predict and identify and fine-tune the treatment based on that. So we have this kind of temporal AMD data for 0 years, 2 years, 3 years data. And the whole idea, what we did is, here there's another challenging part, that we cannot take the full images into the model because the full images are huge in size. Probably many people already know that SD-OCT is a very huge in size, and so we cannot fit that into the images with a very small amount of data. So we got the data from the Harvard clinical trial dataset, but it is large, but compared to like training this kind of complex model, we didn't have enough data. So what we did is actually we extract all the Darson-based features from the SD-OCT images, and we combine the Darson-based feature with the demographic data, like with the demographic data as well as the visual acuity data. So we have demographic, visual acuity, and all the Darson-based features extracted from the segmented Darson from those SD-OCT. So then we again develop this kind of two-layer stack LSTM, where we have the defined time point images as well as their visual acuity, but demographic feature is not changing that much, but visual acuity is changing. So we also have that kind of temporal data. So we parse the temporal data through a temporal model, and we predicted for each time point what is the risk of the patient having SD-OCT in 3 months, 6 months, 9 months, 12 months, something like that. So at defined time interval. But the problem was we faced that, okay, the Harvard clinical trial dataset is a very nice dataset, but it is a trial dataset. So it's very regularly spaced, and this kind of data will not get in the clinic. So putting that kind of model in clinic would be very difficult because they will not follow this kind of clinical trial datasets architecture. So we collected another separate dataset from the real clinic, which is a Miami clinic, and we got also like 799 and 2,854 unique observations, so unique SD-OCT images. So we trained the model only on the trial dataset. We validated the model on the trial dataset as well as this Miami real-life dataset. And we predicted for 3 months, 6 months, 9 months, for different months AMD progression. And we can clearly see that, okay, we had a performance drops on the real-life dataset, but still the performance is quite good, because for 3 months prediction, it's like 0.82. For 6 months prediction, it's 0.87. And we got a very high performance. But as you can see here, for 21 months, our performance really dropped on the real-life dataset in the Miami. This reason is that we lost a lot of follow-up patient for this 21 months. Because of that, actually, the cohort drop, because as you know that in the real clinical scenario, we don't get this kind of like very good and long-term data set. So we, as I also mentioned to you during our metastatic project, that this kind of temporal model has a huge impact on how many number of visits, previous visit you need to make a valid prediction. So here actually for the 3 months, we are varying the previous observations, starting from 2 observations, 4 observations, 6 observations, up to 16 observations. So we can clearly see that if you increase the number of previous observations in the temporal model, the performance started increasing. But at like 10 observations, even if you add more observation, it doesn't really matter because the performance is quite similar. So for 6 months, for 9 months, for 12 months, we see the similar kind of trend that increasing the number of previous encounter for this kind of temporal model, we are getting a high performance boost. So this is actually comparing like other models with our current model. So we have our deep sequence model, which is a red bar. So compare with a traditional random forest, still it is actually using the delta radiomics features. We are subtracting the current feature from the previous feature, and we have the traditional Cox model. So you can clearly see that even if we use the Cox model performs better than random forest, of course, with the delta feature for most of the time point, but our model is performing much better in the Harvard dataset. But when we have the real life clinical dataset, which is the Miami dataset, still we see the similar trend that Cox is performing better, but our model performance is even better than Cox. So I'll end my talk here. I will be open to any question. Thank you.
Well, I would like everyone to unmute their phones and applaud or give virtual applause through the emoji window. Imon, thank you so much. Let's open it up. You're doing, so a big whirlwind tour of great multimodal modeling. I want to open it up for questions.
Angela, I have a question. Sandy.
Hi.
Hi.
Go ahead,
great talk, Imon. And I confess that I kind of spaced out early on because you mentioned something that I didn't quite understand or agree with. So I want to bring up. You had brought up the idea of having. So if you have n tests for something, different kinds of tests, and each test takes in m bits of data to make its decision, you had mentioned the difference between applying the tests separately and just then building a model based on the individual test results versus, I believe, integrating all of the bits of data that go into each test and making a model based on all of them together. Mm-hmm. And then you said, I think, I might have gotten this wrong, that that's more like what physicians do. But they really don't do that. I think they really do the first model, which is they say, well, the patient had test A. Test A says he's got a 50% probability of this. Test B says he's got a 50% probability of this plus something else. And then they integrate that. So can you go over that and make that a little bit more clear for me and perhaps others?
Sure. So I think, sorry, I misspoke or something happened, because what I mentioned is that when I said like physician is used like different types of data, what I meant to say is that the physicians are using different modality, So that's the main thing, that the physicians are making their decision based on different modality stream, right? So finally, when they are making the decision, so that's why I put this picture. I know that this thing will be a bit unclear, that when the physicians are making their final decision, imagine oncologists making their final decision about the treatment planning, about the final diagnosis, they are making the decision based on each of these data streams.
Yeah, okay, that makes total sense. One more quick question, and then we'll give it to somebody else. So when the patients are, let's see, when you have some models that you've shown that take information at different time points. So the patient had test A at time 1, and had test B at time 2, etc. Do you actually use the time difference between the tests in your model, or is it just that they're sequential?
They are just sequential, yes. So that is I completely agree with you. That is the big disadvantage, because some patient has the test in 6 months, some patient has the test in 2 years, and that makes a big disadvantage. But the problem is that if we try to add that kind of information in the model, like how far along the test, but most of the patient doesn't really have the standardized test. So that makes the modeling even more challenging if you don't have standardized tests. So that's why we just make this as a sequential model without taking into account the time gap.
Okay, that's clear. Thanks very much. And see if there are other questions.
Sure.
Anyone else have questions? Oh, or if you want, you can put them in the chat window and I'll read them off. So we have a question from one of the audience members. Were all of these articles just implemented on CT images, or did you use MRI?
So we have a lot of studies on MR, as well as we have studies in mammograms. So they are not CT. The one CT study that I presented is with Matt, where we use the diagnosis of PE from CTI imaging. Yeah.
Okay. Any other questions for people? I'll ask a question, Imon, and as people think about questions. In the study with Matt, you included whole CT images, whereas in the eye exam case, you extracted features from the images before then including in the model. Do you have any sense or guidance as to when it's better to extract features for multimodal inclusion of image data versus using the whole image?
Right. So this is a very interesting question, and there is no standard rule, but one common sense is that if we should use actually 10 times more data than the labels, right? But if we are going with the full CT, so with Matt's study, we have a lot of data. Actually, we pre-trained the model on a very large data set. So that's why we can include the full CT imaging, but with the SD-OCT images, their dimension is very high, where we have very few number of patients and very few time points. So we cannot really go with the full image inclusion in the model. So that's why the most obvious step was to extract the feature, reduce the dimension, reduce the feature space, and then develop the model on the reduced feature space.
So if you had a huge number of images, like you had in Matt's case, and you would have used the whole.
Exactly.
Yeah. Although would there have been a challenge with memory, like the CT data set in his case? That's a volume. I mean, did you get that all into memory, or did you just use subvolumes? How did you?
So we actually use the sliding subvolumes, because that data set also has a slice level annotation. So we use the slided subvolume analysis.
Have you been involved in any projects where there were like particular regions of the image, like organs, and you'd want to just have the model put it there?
Right. So I didn't present it here, but we also are developing an Hcc model where we try to predict the malignancy, Hcc malignancy in the liver, where we know that the Hcc malignancy can only happen within in an abdominal CT. It can only happen within the constrained liver region. So we are putting the model attention in such a way that it will only look at the liver region, not on the whole abdomen volume.
But that's what we think. We think it will only affect certain regions. But what if there's something we just don't know yet? That every time patient has condition A, there's a little spot in the left upper lobe of the lung. A deep learning algorithm will learn that instantly.
Hidden stratification, right?
Yeah, and I think you're right. I think that as we go forward in the march of time, developing these techniques, we have to make sure that they make sense in the context of our current knowledge. But we should also leave the door open a little bit to learn some things about diseases that we don't already know.
Right.
Are there other questions from anyone in the audience? There's
another one in the chat, Daniel.
Oh, sorry. Let me look there. excellent studies. Did the frequency of visits or tests bias the prediction for recurrence?
The frequency of, I didn't put the graph, but you can read the paper, but reviewer asked us exactly the same thing. So we did analyze the frequency of the visit, but it doesn't really have any bias on the recurrence prediction.
And another question is concern for recurrence, is the concern for recurrence increase might, let's see, as concern for recurrence increases, might not more tests be done? So in other words, is that a confounding factor? You know, because if they're, obviously, if the doctor is concerned about the patient having recurrence, they might be doing more tests or have more patient visits, and that might confound the model.
Right. So this is exactly what Daniel suggested when we started doing the metastatic study. Can you build a model just on the number of visits, divided by quarter? But again, we built a model, but it didn't really have any effect. Yeah. But so the number of, because since specialists, we trained on Stanford, we also tried it on Emory because we thought that probably didn't have any effect on Stanford because Stanford is a very specialized kind of hospital. So because of that, actually, we probably don't see an effect. We tried it on Emory where the patient don't leave very often like Stanford, but still the frequency of the visits, especially for this kind of concerning recurrence, it doesn't really have any bias.
What about tests? Because the question also about number of tests.
So I don't know, for test, you mean like imaging test, laboratory test?
Lab could be any kind of test, lab tests.
Radiological studies.
Yeah.
Yeah, so radiological studies we tried, but lab test I didn't, but yeah, we can try it.
So you didn't see an effect on radiology?
Radiology study, no.
Okay.
That doesn't reflect very well on the physicians because you would suspect that they would suspect more and test more, rather than all of a sudden, bingo, you got a recurrence. So it's a little disconcerting, and I think you really have to look a little closer at the density of visits and studies.
Yeah, I will tell you one thing that, for example, in Emory, that many people does the radiology study outside the facility, So they do the radiology somewhere else and just bring the images and the reports with them, So these reports never go into the EHR, but what we find is actually the progress note after the visit actually has the recurrence. So we identify the recurrence from the progress note, not from the radiology report, because the radiology report never goes in the digital database.
So what you're saying is the patient may actually have had more imaging, but
that we are not aware of.
You can't capture it. And it wouldn't be, I guess you get the outside reports in your electronic system, but they don't make it into your model because they're scanned or something.
They're scanned. They are not digital. They are not digital.
So you lose. So that could actually be a signal. Another question from the audience is, how are all the images labeled? I don't know which use case they're referring to, but how do you do your labeling?
So as I said, like here, since we are using the NLP, it's particularly interesting that we have two sources of labeling the data, right? So that's why we can create these huge databases. So first way of labeling is, of course, we hire the experts and they go through the images, they give us the annotation, especially the diagnosis, and also they go through the manual chart review for recurrence, for example, and give us the labels. But the thing is that they can do max to max. So Daniel knows, like in the recurrence project, we hire 4 residents, but max to max, we can get 1,200 cases annotated with recurrence. But that was not really enough for building this kind of deep learning model, because among them, only 30% has recurrence, for example. But still, we selected the cohort in such a way that we'll get high number of recurrence, but still only 30% has recurrence. So we have to have a strategy to increase our training data set. So that's why we use this kind of like NLP generated levels, so that we have a huge database, like 80,000 cases annotated. Like only a few portion is actually expert annotation, and all the rest is actually NLP generated levels. And which is not like 100% perfect, but still we get the levels. Yeah.
I'll just add a question on top of that is, when you're doing the image labeling, are there use cases where there's any question about like whether it's ground truth and you need to have more than one labeler so you can look at variability in labels?
Right.
Or the labels more come from the EMR and you know what they are?
Right. So, for example, recurrence, we don't need a ground truth because the recurrence is established by one of these sources, right? Either through pathology or through radiology or through the progression, right? So we know the recurrence is a ground truth. But for example, P, Matt can tell better that the radiologists actually go through the images and identify not only the diagnosis of P from the reports as well as the images, but also did the slice-wise labeling of the images where exactly they can see P. So we have multiple radiologists actually annotating the same data.
And that is a good best practice, by the way,
Yeah.
when there's any possibility, like particularly for segmentation kinds of tests. Right. Here's another question from the audience, an audience member. Thanks for the insightful presentation. What are the next steps needed to implement this in a usable platform in real time? So that's a translational question.
Right, right.
So particularly for like the recurrence where you want to invoke the palliative care service, so what, I guess the question is, what do you need to do to get it into a clinical usable platform?
Since I left Stanford, I don't have really any influence on Stanford now, but what we are doing in Emory is actually, we already developed a platform in PACS. It's called NIFLR. So if you guys are interested, you can check. That is actually open source. So which actually support real-time running of the machine learning on the PACS images. So we first develop a filter which filters the image based on the studies that you want to identify and the studies where you want to run your machine learning model, and you can run it in a real time, more or less real time, because 30 minutes gap from the real PACS versus this real-time machine learning. And then the main challenge is how to integrate that with the EHR. So we are doing a RTA simulation where we are merging the real-time RTA data like order informations, the progress notes, which are just like 30 minutes delay again, along with images, so that all this machine learning model can be deployed in real time. But it's still an ongoing study, so I cannot really show you any results on that, but we are just like implementing it now.
Another question from the audience is, have you explored synthesizing missing visits and tests? Sort of
Yes.
like automatic query expansion in information retrieval.
Let's see if I can understand the question a little bit better.
Well, I think the issue is, can you impute the missing data using either the query expansion using knowledge to impute additional terms that may not have been specified based on ontological relationships, or if there's other methods of synthesizing a missing visit. So suppose you've got patients who are seen very frequently and others who are less frequent. Can you fill in the missing visits?
This is like very, very challenging problem, of course. So there is not a very easy way to fill up the missing visit clinical notes or imaging data. What we tried actually is that we compare the structured data versus like the clinic notes, and we see that even if clinic note has a lot of missing data, but still the amount or the richness of the data is higher than the structured data. And that's actually also showed in our recurrence cases where we compare the ICD code versus the NLP generated levels, and we clearly show that NLP generated level capture more recurrence cases, even if with missing clinical notes and everything, compared to the structured ICD-9, ICD-10 codes.
Another question, did you look at which patients had utilized guideline follow-up testing for specific cancer? Did such use help in earlier prediction of recurrence?
Right. So exactly that we are doing with one study. But since the audience who posted the question probably already know that it's very difficult to do a long-term follow-up with those patients who has the treatment and doing long-term treatment like hormone therapy. And there is no easy way. Even those patients, as you drop from the treatment, they never come back to the encounter. So ideally, we don't have any of the source of data for those patients. And it's very difficult to track them. And current best practice is that we contact them by phone, we send them surveys, but that doesn't really work because those kind of patients, like involving them in this kind of like regular treatment is very difficult. So what we are trying is we are using social media like Reddit and Twitter to fill the missing data gap from this patient with the EHR. So we are using the EHR data. If the patient has encounter, we'll of course consider the EHR data, but then we are filling the missing data gap through their social media profile, like Twitter and Reddit.
We're just about at the hour. I'll ask one final question, and that is, where do you see the future? What's next? What are either the major unaddressed challenges in building these multimodal models, or where are the next exciting frontiers that you want to pursue in this kind of work?
Yeah, I think the main interesting, there are two very interesting directions for this kind of fusion model. First interesting direction is that, as also the audience asked, that how to deploy this model in the real hospital system. And this is very difficult because, as you know, that every like PACS, the EHR, they have their own kind of like very confined storage, very confined architecture. So doing a real-time integration is very hard for this kind of model. But until we are successful on that aspect, we cannot really deploy this model on real time. So this is the first thing that I really want to work on and improve that part. And the second thing is that the interpretability of this model, because interpretability of this model is even difficult than a single imaging model or single NLP model. So how to do the interpretability for both these branches of the model, specifically if we are trying early fusion or a joint fusion.
Well, I want to thank you, Imon, for this fantastic presentation. Thanks the audience for great questions and great discussion. And we'll see everyone next month. Thank you, everyone, for attending today. And we'll give applause. Give applause
Great
to
talk.
Imon.
Thank you.
Virtual and real. Thank you.
Great talk, Imon. Thanks for your
great
Thank
talk.
you. Thank you.